Hello everyone, I'm Sharli from Artificial Intelligence and Data Science Department of first year, here to explain about few lab experiments of digital system design. Before we get into the concepts, use the website logic.ly for the implementation of the circuits. So let's switch on to the concept. Moving on to the first experiment, our first experiment is all about the study of logic gates. So in this experiment, we will see how to implement various logic gates such as AND gate, OR gate, NOT gate, NOR gate, NAND gate and XOR gate. So basically, what is a logic gate? A circuit that takes a logical decision and process are called as logic gates. So before getting into our experiment, let us see a demo on how to implement circuits using logic.ly. So when you open the logic.ly, your screen looks like this and you are provided with the input controls, output controls and various logic gates towards your left hand side. So I am taking a toggle switch as the input, for example, and I am taking a NOT gate since it's a simpler one. And for output I'm giving a light bulb. So the connections are made. Here, as we know, when your switch is in the off mode, that is your input is 0, your NOT gates inverts the input, right? So you get the output as 1, that is your light bulb glows. So when I turn on the switch, your input becomes 1. So when it goes through the NOT gate, your input gets inverted and your output becomes 0, that is your light bulb doesn't glow. Let us get into our first experiment. Here I have implemented various logic gates, nearly up to 7 gates. So let us verify their outputs. For verification, we require the truth table of the logic gates. At first I have implemented the AND gate, and for AND gate, the output is high when both the inputs are high, and the output is low level when any one of the input is low. So as per the truth table, when both the inputs are 0, your output is 0. And when I give 0 and 1 as the input, the output is still 0. And when I give 1 and 0 as the input, the output is still 0. And finally, when I give the inputs as 1 and 1, your light bulb glows. That is, your output is 1. In the same way, let us verify the outputs for the OR gate. As we know the truth table, when both the inputs are 0, the output is also 0. And when I give the input as 0 and 1, the output becomes 1. And when I give the input as 1 and 0, the output is still 1. And when I give the input as 1 and 1, the output is also 1. So moving on to the NOT gate, as we saw in the demo, when your input is 0, your output becomes 1. And when your input is 1, your output becomes 0. Then we have implemented the NAND gate, two input NAND gate. NAND gate is nothing but the combination of the AND gate and the NOT gate. So as per the truth table, when both the inputs are 0, your output is 1. And when you give the input as 0 and 1, your output is still 1. And when you give the input as 1 and 0, your output is 1. And finally, when you give the inputs as 1 and 1, your output is 0. So next we have implemented the NOR gate, which is just the combination of the OR gate and the NOT gate. So as per the truth table, when both the inputs are low, that is 0 and 0, your output is 1. When the inputs are 0 and 1, your output is 0. And when the inputs are 1 and 0, your output is still 0. And when the inputs are 1 and 1, your output is 0. Now let us verify the outputs for an XOR gate. When both the inputs are 0, the output is also 0. When the input is 0 and 1, your output is 1. And when your input is 1 and 0, your output is 1. And when the inputs are 1 and 1, your output is 0. Coming to the 3 input NAND gate. So when all the 3 inputs are 0, your output is 1. When your inputs are 0, 0 and 1, your output is 1. In the similar way, when all the inputs are 1, your output becomes 0. By now, we have implemented various logic gates and thus we have finished our first experiment. So our second experiment is all about the study of adders and subtractors. So in this experiment we will see how to design adders and subtractors. In adders we have two types of adders, half adder and full adder. In subtractors we have two types of subtractors, half subtractor and full subtractor. Now let us see the implementation of the half adder circuit. Half adder circuit consists of AND gate and an XOR gate. As we know, we have designed this based on the sum equation and the carry equation. So the sum equation is given by A exclusive B and the carry equation is given by A into B. As per the truth table, if both the inputs are 0, your sum is 0 and your carry is also 0. And if your input is 0 and 1, your sum is 1 and your carry is 0. And when your inputs are 1 and 0, your sum is 1 and carry is 0. And when your inputs are 1 and 1, your sum is 0, your carry is 1. So this is your half adder circuit. I have designed all these circuits based on the circuit diagram, and let us see how the input and output operation works. So moving on to the full adder circuit. A full adder circuit generally consists of the XOR gate, AND gate and OR gate. So sum equation is given by A exclusive B exclusive C and our carry equation is given by A plus B into C plus AB. So this is our sum output and this is our carry output. As we know our truth table, when all the inputs are 0, our sum is 0 and carry is 0. When our input is 0, 0, 1, our sum is 1 and our carry is 0. Whenever your input is 0, 1, 1, your sum is 0 and carry is 1. Whenever all the inputs are 1, the sum is 1 and the carry is 1. Generally, a adder consists of the sum and carry as the outputs, and for the subtractor, the outputs are the borrow and difference. So over here, now let us discuss about the design and implementation of a half subtractor. A half subtractor generally consists XOR gate, AND gate and an OR gate. So there are two equations, the borrow equation and the difference equations. And the borrow equation is given by A dash B and the difference equation is given by A exclusive B. So this is your difference equation, your difference output, and this is your borrow output. So when both the inputs are 0, your output is also 0. And when your input is 0 and 1, your borrow is 1 and the difference is 1. And when your input is 1 and 0, your borrow is 0 but your difference is 1. And when the inputs are 1 and 1, your borrow is 0 and your difference is 0. We had earlier seen about the design and implementation of a half subtractor, and now we are going to see about the design and implementation of a full subtractor. A full subtractor generally consists of an XOR gate, NOT gate, AND gate and an OR gate. So this output is given by the difference and the borrow equation, where the difference equation is A exclusive B exclusive C and your borrow equation is C into A exclusive B the whole dash plus A dash B. So when all the inputs are 0, your borrow is 0 and your difference is 0. When your inputs are 0, 0, 1, your borrow is 1 and your difference is 1. When you give all inputs as 1, your borrow is 1 and your difference is 1. Let me give some other inputs like 0, 1, 1. Your borrow is 1 and your difference is 0. So thus we have seen the full subtractor design and implementation. Now we are going to see the experiment 3, that is the design and implementation of the code converter 1. So in this experiment we will see how to implement the binary to gray code conversion and the gray code to binary conversion. The first circuit depicts the binary to gray code conversion and your second circuit represents the gray code to binary conversion. So let's see the binary to gray code conversion first. If all the binary input are 0, your corresponding gray code output is also 0. So let us give the binary input as 0, 0, 0, 1. So your corresponding gray code output is also 0, 0, 0, 1. Let us give some other binary input like 0, 1, 1, you get the gray code input as 0100. So let us give all the binary input as 1 and you get the corresponding gray code output as 1000. And if you give the input like 1001, your corresponding gray code output is 1101. So next, coming up to gray code to binary code conversion. If at all we give the inputs as 0, your output, that is your binary output, is always 0. So if at all you give the gray code input as 0001, your binary code output is 0001. So if you give some other outputs like 0111, your corresponding binary output becomes 0101. And if you give all inputs as 1, you get the output as 1010. So our next experiment is experiment 4, that is to design and implementation of a code converter 2. So in this experiment, we will see how to implement BCD to XS3 code conversion and XS3 to BCD code conversion. This circuit design depicts the BCD to XS3 code conversion, and when all your BCD inputs are 0, your corresponding XS3 output is 0011. And if at all you give the inputs as 0001, your corresponding XS3 output is 0100. And if you give the inputs as 1001, your corresponding XS3 output is 1100. And if you give the inputs as 0111, your corresponding XS3 output is 1010. Likewise, you can just operate the corresponding input for the BCD and your output will be shown in the XS3. So now we are going to see the XS3 to BCD code conversion, out of which your inputs are the XS3 input whereas your corresponding outputs are the BCD output. If at all your inputs is 0000, your output is 0101. If your inputs is 0001 and your outputs is 0110. If at all your inputs is 0100, your output is 0001. And if at all you give some other inputs like 0110, your output is 0011. So let's discuss about the fifth experiment, which is nothing but the designing and the implementation of the parity generator. So in this experiment, we will see the implementation of the parity generator. Parity generator is of two types, odd parity generator and an even parity generator. This circuit diagram shows the parity generator, out of which the first output is the even parity and the second output is the odd parity. Even parity is given by the equation A exclusive B exclusive C, and the odd parity is given by the expression A exclusive B exclusive C the whole dash. So when all your inputs are 0, your even parity is 0 and your odd parity is 1. If at all you give the inputs as 001, your even parity is 1 and your odd parity is 0. And if you give the inputs as 011, your even parity is 0 and your odd parity is 1. And if you give the inputs as 111, your even parity is 1 and your odd parity is 0. So the last experiment is our experiment 6, which is to design and implement of multiplexer and demultiplexer. So in this experiment, we will see how to implement multiplexer and demultiplexer using the logic gates. What is multiplexer? A multiplexer combines many input lines and produces a single output line. What is a demultiplexer? A demultiplexer, it takes one input line and directs them into many output line. This circuit diagram shows 4 to 1 multiplexer, out of which D0, D1, D2 and D3 are the 4 inputs and S1 and S0 are the 2 selective inputs, out of which one output line is directed. So when both of your selective inputs are 0, your D0 is activated. So your output is 1. When your inputs, the selective inputs are 0 and 1, your D1 is activated. So your output is 1. So when your selective inputs are 1 and 0, your D2 is activated, so your output is 1. And when your selective inputs are 1 and 1, D3 is activated so that your output is 1. So this is the 4 to 1 multiplexer. This circuit diagram shows the 1 to 4 demultiplexer, out of which the first input is the single input taken and the rest two are the selective inputs S1 and S0, and these four are the output lines. So when your input line is 1 and the selective inputs are 0 and 0, your output is 1. That is, your I0 is activated. And if your selective inputs are 1 and 0, I2 is activated. And if your selective inputs are 0 and 1, I1 is activated. And both the selective inputs are 1, your I3 is activated. In this video, we have seen how to design and implement various logic gates and combinational logic circuits using logic.ly. Hope you like this video. Thank you guys.